Everyone, today we're going to conclude our discussion on amines by discussing the spectroscopy of amines. So, like alcohols, amines absorb in the 3300 to 3500 range in the IR spectroscopy. Depending on the classification of the amine, this can affect the signal. If we have a primary amine, we have two signals. We have the symmetric stretch, where both the hydrogens are going to be stretching in the same direction. And then we also have in opposite directions, the asymmetric stretch, where each hydrogen will be moving in the same direction when they stretch, right? So this gives us a signal around 3350 and 3450 inverse centimeters. We get a double peak because we have both these signals. In a secondary amine, we have one signal around 3350 inverse centimeters. And then tertiary amines, there's no signal because there's no hydrogen bond for the stretch to be in this range, right? And so these are going to be a little bit less intense, meaning the signal is not as large than alcohols, but it'll be more sharp. It'll be a sharper signal than alcohols. In NMR or proton NMR, these are difficult to detect because amines appear in a wide range all over the NMR spectrum. If you have an amine, it is by deuterating the sample, which means just replacing hydrogen with deuterium, which is an isotope of hydrogen, and then the peak in the proton NMR will then disappear. The amine peak disappears. If we're looking at protons adjacent to the amine, then they are shifted downfield because of the electron withdrawing effect of the nitrogen. So these protons here will be shifted downfield because of electron withdrawing effects. And so if it's looking at an alkyl group, then you'll have a integrated three proton singlet that'll be about 2 to 2.6 delta. Right, so if we have something that looks like this on a methyl group, CH3, whatever this will give you a 3 proton singlet at around 2 to 2.6 delta or ppm. That's because of electron withdrawing effect, and it doesn't couple to the amine proton. Be characteristic of an N-methylamine. In the carbon-13 NMR, carbons bonded to the amine are shifted about 20 ppm or delta downfield from other alkyl carbons. So if we had something like cyclohexane, amine, cyclohexylamine, or this would be N-methyl cyclohexylamine or cyclohexanamine, then this carbon-13 would absorb around 33.4, and this would absorb around 58.7, which would be about a 20 ppm downfield shift. Whereas these ones, all around, will be around the 23 to 30 ppm range, right? So we're comparing these carbon values to that of the one that's bonded to the amine. So that's how it's just distinguishable in carbon-13 NMR. But again, amines are kind of hard to distinguish in NMR. Okay, so let's see a quick example. Or actually, before we go into an example, let's talk about mass spec. And so the nitrogen rule of mass spec says that a compound with an odd number of nitrogen has an odd molecular weight. And so this is because nitrogen is going to be trivalent. And if nitrogen is trivalent, that means that we have 3 bonds coming out from this nitrogen. We have an even molecular weight. That means that we have 0 or 2 nitrogens. An odd molecular weight is 1 or 3 nitrogen. So just by looking at the mass spec and looking at the molecular ion peak, we can determine this. Alcohols and carbonyl compounds, we see an alpha cleavage with amines. So if we have an amine, this would be the alpha carbon, and we get cleavage between the alpha carbon and whatever else is there. And so this means that if we have 2 mass spec peaks, that we have a secondary amine. If we have 3 mass spec peaks, then that means that it is a tertiary amine. And 1 mass spec peak means that we get a primary amine. All right, so here we see that both of these, the molecular ion is at 87, which is right there. And then at both of these, we have 2 alpha cleavage sites. The cleavage on the left here is going to be a resonance stabilized amine. So the one possible cleavage, let's rewrite this here. These are the 2 alpha cleavage sites. If we cleave here, that'll give us CH3 radical, and then the HN imine stabilized 1, 2, 3 carbons, 2, 1, 2, 3. Or if we cleave here, we'll get a CH2, CH3 molecular ion with HN double bond C, positive charge there, positive charge here, 1, 2, right? So those are the 2 different alpha cleavage peaks that we'll see. This peak is going to correspond to the 58 atomic mass because it's smaller. This will correspond to the mass number of 72. And so the alpha cleavage gives us resonance stabilized ion that then can fly through the mass spec, and it gives us unique signals. And so the main one we're looking at here is going to be the alpha cleavage peaks. And so that's the mass spec of amines, the IR, and NMR. So let's look at an example problem here. We have a compound A that has a molecular formula, CH6H12O, and then it has an absorption peak for IR around 17, 15 centimeters. So this looks like an aldehyde or a ketone peak. So if we have 12 protons, that means that it's the same number of protons as benzene. So I'm thinking it'll be a pentene ring that has an aldehyde peak and then double bonds throughout the rest of the structure, because that gives us 1, 2, 3, 4, 5, 6. Sorry, I mean, we have a 6 carbon and 1 oxygen. That means we should have 2 protons at each position. So I'm thinking that it'll be a pentane ring, not a benzene type ring, where we have an aldehyde. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're still missing 2 protons here. Let's see if we then change this to an alcohol, then we may have the correct number of proteins just on a cyclohexane. If we take a closer look, we see that whatever it's treated with is ammonia and sodium borohydride. If we treat something with ammonia and then sodium borohydride, that's going to be reducing. What are we going to be treating with ammonia? Well, if this has an absorption peak around, so if the first compound A, has an absorption peak around 1715, that means that it's most likely an aldehyde or a ketone. And we know that an aldehyde or ketone, if we're treated with ammonia, can be converted into an imine, like so. And if it's converted into an imine and then reduced with sodium borohydride, then it'll get reduced into an amine. And so that gets reduced into an amine. So that's how we're going to generate our amine here. If we look at the IR spectra, we see that this is an amine peak or peaks. And if we have 2 peaks, that means that it's going to be a primary amine. These look like CH2 stretches right there. And if we look at the NMR spectrum, we see that the broad peak here has a relative area of 1 for the proton NMR. And then we have what looks like a singlet at around 0.8 ppm, and then it looks like a doublet around 0.98. I was thinking that it would be something like 1, 2, 3, 4, 5, 6, and an aldehyde here, and this could convert into an amine like that, according to the reaction conditions. But when I look at the NMR spectrum, it tells a slightly uh, different story in this case now. And so I see that we have 9 different protons that are all at the lowest signal. And whenever I see that, that makes me think that this is going to be a tert butyl group, right? Because that means that if we have a tert butyl group, each of these protons here will have the same chemical environment. And so that's why it would integrate to 9 here. Then we have 5 protons Um, After that, they're going to be in a similar chemical environment as well. And if we have 5 protons that are in a similar chemical environment, we use our degree of unsaturation, which is DOU, which is useful for NMR. It'll be 2 times the number of carbons, so 2 times 6 plus 2 minus the number of hydrogens, which is 12, plus the number of nitrogens, which is, well, for the first compound, that would be 0, and divide this by 2. This will give us 0, and for the second compound, we get 2 times the number of carbons, which is 6, plus 2 minus the number of hydrogens, which is 15, plus the number of nitrogens, which is 1, divided by 2, and that will give us, we also get 0, so there's going to be no double bonds, which should help simplify our structure a little bit. So know that the carbon bonded, or the protons bonded to the carbon that's bonded, these are going to be shifted downfield because of the electron withdrawing effect of nitrogen, and we see that that signal here is going to be 1, which means that if we had a ketone instead, when we go through the reduction, we will end up with a single extra hydrogen there that is bonded to the amine. The specific value of the amine protons are less known, so we don't really know where they're going to be. And so these could be close to the protons that are on this methyl group here. And we know we have the tert-butyl because we have the 9 protons there. So I believe that the structure, putting all this together, would be NH2, so this would be 1, 2, 3. It would be 1, 2, 3. It would be 1, 2, 2 trimethyl propanamine is what this structure would be. And the original structure that we were going from was 1, 2, 3, 4. So 3, 3, or 1, 2, 3, 1, 2. So put the ketone on the smaller one, it'll be 1, 2. So it'll be 2, 2 dimethyl butanone, right? So this will be the final structure. And combining the IR, which we know that it has to be a primary amine, and then the fact that that one proton that's shifted downfield is going to be the one on the carbon that's bonded to the nitrogen itself. So that's how we would determine this. So that would be our conclusion for the spectroscopy of amines. We went through an example. We did the mass spec showing the alpha cleavage is the predominant ion creating mechanism here for mass spec. And we talked about how amines have similar IR spectroscopy to alcohols, just less intense, but sharper peaks. And then depending on the degree of the amine, that tells us a little bit about the shape of the peak, whether there's double, single, or no peak at all. And then how proton NMR is hard to distinguish. Amines and carbon-13 NMR is also likewise. So that'll be it for our discussion on amines. Next, we'll talk about biomolecules.